Have you ever wondered how Netflix recommends movies that perfectly match your taste, or how your email filters out spam? These are not mere coincidences or random choices by a machine. They are the result of sophisticated algorithms working tirelessly behind the scenes. This is the realm of machine learning, a domain where computers learn from data to make decisions and predictions. One such algorithm, camouflaged within the labyrinth of machine learning, is the multilayer perceptron. It's like a diligent worker in a factory line processing information, making connections, and churning out results that affect our daily lives. From powering recommendation systems to enhancing cybersecurity, these multi-layer perceptrons are the invisible force behind many technological wonders we often take for granted. So the next time you marvel at a personalized playlist or an uncannily accurate predictive text, remember, there's a multi-layer perceptron working its magic behind the scenes. The secret underlying these marvels of technology is a concept known as the multilayer perceptron. So what exactly is a multilayer perceptron? You might ask. Well, let me unravel this intriguing concept for you. Picture a group of interconnected nodes, akin to the complex network of neurons in our brain. This is the basic structure of a multilayer perceptron, often shortened to MLP. Now, an MLP is a type of feed-forward artificial neural network. The term feed-forward here means that information in this network only travels forward from input to output, with no loops or cycles. Imagine a one-way street where traffic moves in one direction only. That's how the flow of information works in an MLP. An MLP consists of three main components: an input layer, one or more hidden layers, and an output layer. The input layer is where we feed in our data. This data can be anything: a photo of a cat, a song, or a tweet, depending on what we want our MLP to analyze. This data then travels through one or more hidden layers. These layers are the real magicians behind the MLP. Each layer is made up of a set of neurons or nodes, where each node is connected to every node in the next layer. These connections, or weights as they're often called, are where the learning happens. They adjust and fine-tune as the MLP learns from the data it's fed. Finally, we reach the output layer. This is where the MLP presents its findings. If we fed in a photo of a cat, the output layer might tell us whether the photo indeed contains a cat or not, or if we fed in a song, it might classify it into a genre. But how does an MLP learn to make these decisions? It uses a process called backpropagation, where it learns from its mistakes by adjusting the weights of the connections between the nodes. In essence, a multi-layer perceptron aims to mimic the human brain's decision-making process. It takes in information, processes it through a series of complex connections, learns from its experiences, and makes a decision. Sounds pretty human, doesn't it? You might be curious about how a multi-layer perceptron works. Well, let's dive right into it. Picture this. A multi-layer perceptron is like a factory assembly line. The raw materials, in this case, are our input data, which are fed into the initial stage of production, the input layer. This input layer is the first point of contact for our data. It's where the raw data is ingested and prepared for further processing. The data can come in any form: images, text, numbers, you name it. This raw data is then converted into a format that the multi-layer perceptron can understand, which is essentially an array of numbers. Once we have our data ready, it's time for it to move further down the assembly line to the hidden layers. These hidden layers are where the magic happens. They are composed of multiple nodes, and each node holds a weight. Now you might wonder, what's the function of these weights? These weights are like filters that determine how much importance should be given to a particular input. As the data passes through each hidden layer, it gets multiplied by these weights, and an activation function is applied. The activation function is what decides whether a node should be fired or not. It's like a quality check in our factory analogy, deciding whether the processed part is good enough to move to the next stage or not. Finally, the processed data reaches the last stage, the output layer. This is where we get the final result. The output layer can produce a single output or multiple outputs, depending on the problem at hand. Now, I know this might sound a bit complicated, but remember, it's just like a factory assembly line. The raw data comes in, gets processed through various stages with different weights and activation functions, and finally, we get the desired output. In essence, the multi-layer perceptron is a complex system performing a simple task. It's all about taking raw data, processing it, and giving us useful output. Simplified, it's all about assigning the right weights to make accurate predictions. Like any technology, multilayer perceptrons come with their strengths and weaknesses. Diving right into the power of multilayer perceptrons, let's talk about their ability to model complex, non-linear relationships. Imagine trying to predict the weather. There are so many factors at play: temperature, humidity, wind speed, pressure, and more. These factors don't interact with each other in a simple, straight line. They mesh together in complicated, non-linear ways. That's where multi-layer perceptrons shine. They can capture these complex interactions, making them a powerful tool for tasks like weather prediction. But it's not just about weather. From speech recognition to image classification, multi-layer perceptrons are behind some of the most advanced applications of machine learning we see today. They're like the Swiss Army knife of machine learning algorithms, versatile, robust, and capable of tackling a wide array of problems. However, every rose has its thorns, and multilayer perceptrons are no exception. One of their main pitfalls is their susceptibility to overfitting. Overfitting is like memorizing answers for a test instead of understanding the concepts. A model that's overfit will perform excellently on its training data but fail to generalize to new, unseen data. It's one of the main challenges faced when training multilayer perceptrons. And speaking of training, it's not a walk in the park. Training multilayer perceptrons can be computationally expensive and time-consuming. It's like trying to solve a giant puzzle where each piece affects all the others. You have to adjust the weights and biases of all the neurons in the network simultaneously, and this can take a lot of computational power and time. But despite these challenges, the power of multilayer perceptrons cannot be understated. They have revolutionized the field of machine learning and continue to be a popular choice for many complex problems. Thus, while powerful, multilayer perceptrons require careful handling. Let's look at some real-life applications of multilayer perceptrons. First off, let's delve into image recognition. Multilayer perceptrons are the backbone of this technology. When we upload a photo to social media and it automatically tags our friends, or when our phone unlocks just by recognizing our face, we have multilayer perceptrons to thank. These complex networks are trained with thousands of images until they can identify patterns and features that distinguish one face from another. They can also recognize objects, handwritings, and even emotions in images. Next, consider speech recognition. Ever wondered how your virtual assistant understands your commands, or how you can dictate a text message instead of typing it? Once again, multilayer perceptrons are at play. These networks process audio data, breaking down the complex patterns of human speech into simpler elements. They're trained to understand different accents, tones, and even languages, making our interaction with technology more seamless and intuitive. Now let's turn our attention to medical diagnosis. Multilayer perceptrons are revolutionizing healthcare by aiding in the detection and diagnosis of diseases. They analyze medical images, such as MRI scans or X-rays, to identify anomalies that could indicate a health concern. By learning from thousands of medical images, these networks can spot the tiniest variations that might be missed by the human eye, potentially saving lives in the process. It's important to note that while these applications are impressive, they're just the tip of the iceberg. Multi-layer perceptrons are used in countless other areas, from weather prediction to financial forecasting, and even in the creation of art. These networks learn from vast amounts of data, identify patterns, make predictions, and help us make sense of the world around us. As we can see, multilayer perceptrons have a broad range of applications, making them a cornerstone of modern machine learning. So what have we unearthed about multilayer perceptrons today? We've delved into the world of machine learning and discovered the multilayer perceptron, a type of feed-forward network. We've seen how it functions, inputting data, processing it through hidden layers, and producing an output. We've also explored how it can learn and adapt, adjusting its weights and biases to minimize errors and improve results. We've examined its advantages, like its ability to tackle complex problems and model non-linear relationships. But we've also acknowledged its pitfalls, such as the risk of overfitting and the challenges of training large networks. And of course, we've looked at real-life applications. We've seen how multilayer perceptrons can be used in everything from image recognition to predicting stock prices. So next time you're marveling at a technology, remember, There's likely a multilayer perceptron working its magic behind the scenes. Next time when Netflix recommends your new favorite movie, remember it's all thanks to the multilayer perceptron working behind the scenes.